today about how repetition of force can actually progressively decrease the tolerance of the tissue, or may prevent significant recovery that's required. So we'll get into the physiology of the muscles a little bit to talk about that as well. So basically, injury risk is proportional to the balance between the demands on a tissue and a capacity. Here we might have a large tissue like the quadricep muscles or shoulder deltoids that have a fairly high capacity and can withstand a fairly high demand before that balance is tipped and there's a significant risk of injury. Smaller tissues, of course, have smaller capacities and can withstand smaller demands. But this capacity demand relationship's more complicated than just this sort of teeter-totter that I show here. In actual fact, tissues in the body act more like this. We see most tissues have sort of a nonlinear exponential curve where, and just to orient you to this would be sort of increasing frequency from left to right. So maybe doing a bicep curl. And this would be the load that you would be holding or would be applied to a tissue. And so we have this sort of fine line here, which will define the area between what is acceptable, where the capacity is greater than the demand, and what is unacceptable. And what you notice is the capacity actually decreases as the frequency goes up. So for example, if I said I wanted you to give me your maximum bench press and you're to do that once, you might be able to do that with 150 or 250 pounds or whatever. But if I asked you to pick a load that you could do 15 or 20 times repetitively, you would have to pick a lower load because of the fatigue that would start to occur. And so when we load things above their tolerance at low frequencies, we tend to think of these as accidents or acute injuries. But most of what we see in the workplace are repetitive strain injuries where tissues are loaded repetitively. It should be noted as well that once every tissue in the body has a different curve, every person has different curves. Those change throughout your life. If you decide to go start weightlifting, you can start to shift this curve up and to the right. If you have an injury, that curve might now move downward to the left. And the whole art and science of rehab would be to get you as close to this line to start to build the tissues up so that it can start to recover and move back to where it was or even beyond that. So assessing risk is determining where we are on this curve. So for example, at a moderate frequency, we're above the curve here. That would be considered to be unacceptable. And maybe even at a higher frequency, very low load might be considered to be acceptable. And what I want to talk about today is how to determine what this curve looks like and how to determine where it is for various tasks. Some tasks, we have good repetition data and psychophysical data to tell us how this curve looks. Other tasks, we only have strength data up here, but I'll show you how we can correct that strength data to try to make determinations of acceptable loads. I'm just going to kick out for a second just to see I'm on the right track, because again, I still can't hear anything. Okay. Sorry about that. I just want to make sure. I can't hear anything, so I want to make sure I'm not talking to myself here. Okay, so this slide just sort of represents the fact that, things in the workplace are not cut and dried. And we have a range of tasks that are of quite obviously very high risk. And we have other tasks that are quite obviously great designs and have very low risk. But we often need to determine what this line looks like, and we need to sort of determine our line in the sand. And so we need to take sort of this gray world, and we need to make it black and white. And this becomes our line here that will determine what is acceptable and what is unacceptable. We don't necessarily talk about what is safe or unsafe because any task has some risk associated with it, but typically we determine that line by saying we want to design for 25% the 25th percentile female, so all but the weakest 25% of females, or a 5th percentile male. We have to set those lines before we start this analysis. So let's just quickly kind of go through the upper extremity anatomy. I'll talk some about the peculiarities of the tissue. So essentially we have everything down from the shoulder made up of the clavicle, scapula, and the top of the humerus. We have an elbow joint which has its own risks associated. We have an ulna and radius that can rotate in concert to cause pronation and supination. We have flexion, extension, radial and ulnar deviation at the wrist. And then we have very small muscles and tendons which can be loaded quite heavily due to the fact that most of the force is generated in the forearm. I'll show you on the next slide. And so these regions all have their own risks associated with them. One of the big problems is that For example, if we look at the palm of the hand and the forearm, these are the muscles that actually run through the carpal tunnel. So here's the carpal tunnel here, has long tendons that run to the fingers. So these forces can be very high because they're generated by fairly large muscles distal from the area that they're acting. We look at the back of the hand here, we see a similar architecture, another retinaculum on the extensor side. And shows very well the very large muscles inserting on a very small area. And when we have a lot of force applied in a small area, we call that pressure or stress. And this is why we can get things like lateral and medial epicondylitis, because we can get fraying of the tendons here from the very large forces being generated in the forearm being exerted at a small area. So this schematic just sort of shows where some of the risks lie. I mean, so typically we will have a muscle that will have some sort of tendon which attaches it to the bone. So the tendon is the part that attaches the muscle to the bone. When we have longer tendons like these ones here, they need to be protected in certain areas where there may be rubbing and friction. And so typically there'll be a synovial sheath, which is a very lubricated sort of tube that protects the tendon. It can slide through it quite nicely. In other areas like the shoulder, where there's not enough room for long tendons and the muscles more or less attached straight to the bone via very small tendons, we'll protect the muscle from the bone with these sort of bursa sacs. And so all of these things can become inflamed. You can have the tendinitis, an inflammation of the tendon, tenosynovitis, an inflammation of the synovial sheath, and bursitis, an inflammation if this is being rubbed on too much. So where are some of these bursa? Well, we have them up in the shoulder. You can imagine then if this humerus was rotated far enough around that it would pinch this bursa, and you can start to get a breakdown of it. We also have some other peculiarities in the shoulder in that all of these nerves and blood vessels pass through what's called the thoracic outlet, and they pass below the scapula and underneath the pectoralis minor. So if you raise the hand up, these can kind of be bent around those areas and start to get rubbing on them as well. So that is an injury that precipitates itself up in the shoulder, but can actually be felt even down at the wrist. And we can also get tendinitis in the shoulder of these sort of flat, short tendons that join the rotator cuff muscles. And these are the types of tasks that you see that tend to cause these types of things. At the elbow, we have, again, like I said, these very large muscles inserting on the lateral epicondyle, so for the extensors, and for the flexors on the medial epicondyle, so we can get inflammation there. See this from things like hammering or just overuse. And then we'll talk a little bit about what's going on in the hand here. So in the hand and wrist, we have a series of 5 tendons which are going to each of the fingers, and they pass through what is called the carpal tunnel. There's bones on the bottom and a retinaculum on top, and the biggest problem here is that the median nerve also passes through here, innervating these various digits. And so if there's inflammation, which I'll show on the next slide, if we get inflammation of the sheath here, then there ends up being pressure on the nerves. So this sort of demonstrates once these tendons have been inflamed because you've flexed the wrist, let's say, and they're constantly rubbing over the sheath, once they get inflamed, then there's a lot of pressure on the nerve. And typically, most of the sensory portion of the nerve is on the outside and most of the motor portion is on the inside. And so you tend to, as it breaks down, you tend to get sensory deficits, some numbness in the fingers. And then as it becomes worse and worse, you start to get some motor deficits and even some atrophy of muscles like the thenar muscles. We can also have this is essentially a tenosynovitis issue, but it has a peculiarity with this nerve passing through here. We also have, this can happen with trigger fingers, so these tendons can get inflamed and the sheaths can get inflamed and your finger can be locked, or even what they call sort of the anatomical snuff box, how you kind of retract your thumb. There's a sheath here too, which can also become inflamed. Okay, again, I'm just going to double check that I'm on the right track here. Okay, so I want to quickly talk about how we can measure demands in the workplace, because I'm going to show you some very specific data for pinches, grips, pronation, supination, and sometimes it's not just important to know what kind of pinch grip someone can do, but you also need to know what those demands would be in the workplace. So there are all kinds of devices available, Chatillon gauges, Mark 10 gauges. Each one can come with a series of adapters, hooks, grips, that you can simulate the hand, various interfaces that you can screw into things. So one way or another, you can determine sort of the pinch forces or the grip forces or the pull forces that might be required. Um, and then, for anybody that does this kind of thing, I can provide this spreadsheet. Basically, we've developed a spreadsheet that will try to determine whether or not a given test. So, for example, let's say we're measuring a grip force on various parts. Those parts will have some variability to it, and we might have a series of them being 20, 25 pounds or kilograms here. And basically, what this spreadsheet does is, first of all, determine whether there were any. Maybe you slipped, and there's an outlier here that can be removed. So it sort of mathematically and statistically determines that. And so here you can see that very high force would be rendered to be, I won't get into the specifics of how this is calculated, but be determined to be an outlier. So the average forces would then be calculated with everything but this blacked out force. We would say, okay, well, that mean force is 22.9. It would also determine how variable your measurements were, because you want nice, reliable measurements of these parts. If the variability is too high, we've just arbitrarily set a limit of 20%. If it's higher than that, you'd say, well, that wasn't a reliable test. We need to get some more parts or make some more measurements and try to be more consistent. You can also then input what your limit is. So I'm going to show you how to determine what those limits might be at various frequencies. And then once it determines what the average force is for those parts, it can determine whether or not that force, 22.9, does indeed exceed the limit of 15. So here we would say, well, yes, indeed, it was a reliable test, but in fact, the force was too high. So there are ways to do this in terms of getting good, reliable actual force levels. Um, And so the next thing, what I want to talk about for the rest of this presentation is how to determine tissue capacity. And that becomes an issue when we want to do things repetitively. I'm first going to show you the wealth of strength data that's out there. But again, people do things repetitively, and it's very rare that somebody just does something once a day. So how do we account for that? And that's probably why most of you are tuning in to kind of learn how to handle what the more common condition, which is repetitive efforts. But let's start with the strength data, because the method I'm going to show you can actually take strength data and correct it to account for repetitions and durations. So let's start at the shoulder and elbow. There's some software available to do this. The shoulder is a very complex joint, and it's not always easy to determine what the moments are at the shoulder and then also what the strengths might be in various positions. So I'm just going to quickly go through sort of how the 3D static software works. Many of you may have used that in the past. It basically breaks the body into a mannequin of rigid links with sort of hinge joints. The shoulder can flex and extend, or forward and backward it's called, abduct to the side, and also internally and externally rotate. We have flexion at the elbow, and it actually even has a wrist joint in it now, and it can determine strength demands at the shoulder. So basically, you need to define, one of the things about strength is it's actually dependent on joint angles. And I won't get too much into details, but essentially muscles, the strength of a muscle will actually depend on how long it is. Most muscles have a rest length. You can actually imagine most rest lengths being kind of right around the position you'd be in if you got in the fetal position. So if you stretch a muscle beyond that or shorten it beyond that, it actually becomes weaker. So in any method to try to predict, for example, shoulder strength, it's important to know not only what the shoulder angle is, but also what the elbow angle is, because things like the bicep cross both joints and can influence the strength. And so this mannequin then gets broken into a series of angles, and I'll just quickly show you how it's defined in 3D static. This would be more or less the extension angle. A shoulder angle, which is defined as going from the hip to the shoulder and the shoulder down to the elbow. A trunk angle, which is defined as the angle between the thigh angle and a trunk between L5S1 and the shoulder, and then a hip angle as well. So in the software, there are many equations to determine what the strength would be at each of these joints. And basically, this is a page from Chaffin and Anderson's textbook, which shows you the nature of these equations. There's some things that are important in this, and I'll do a little bit about statistics so you understand that. So for example, I'll show this in more detail, but I think these were originally done in inch pounds, so this would be to correct it for males and females. Also, this gives us an idea how much variability there was, because we typically don't want to know what an average person could do. We might want to know what 75% of people could do, and I'll get to that in a minute. So if I blow this up a little bit, you can see, for example, elbow flexion is not only dependent on elbow angle squared, but also shoulder angle because the elbow flexion strength is very dependent on the bicep, and the bicep crosses both of those joints, so its length will be dependent on both of those. Things like torso flexion, standing, will be dependent on torso angle and torso angle squared. So this is a little bit of what's going on underneath the hood in the software. And the nice thing about it is it does all the calculations for you. And there's other software out there, Jack and Dassault and other software that can do this. So just to give you an idea of, for example, how elbow strength changes with joint angle, we typically get this inverted U with muscles. The elbow is strongest around 90 degrees of flexion, and you can see it drops off on either side. Here's the male with here's with the elbow angle changing with the shoulder angle at 0, sort of at your side, and you get a sense of how much higher the strength is for males than females. On average, in the upper body, it might be 2 times, maybe. It really is quite joint dependent. We can again see that shoulder flexion strength decreases as you become more flexed at the shoulder, so kind of raising the arm in front of you. And again, we can see the gap between males and females if we look, let's say, with the elbow fully extended, and it drops even more if the elbow is bent to 90 degrees. So this is kind of what those equations look like under the hood. I'm just going to stop here to see if there's any particular questions. Okay. Margot, I'm just going to give you a phone number to call if you need to get a hold of me. And I'm going to carry on. Okay, so uh, people tend to get very bored with stats, but I do want to it's very important to understand how we would do an experiment, for example, to figure out, what someone's pinch strength would be. In that experiment, we would get a range of values from people that would go from the weakest to the strongest. And there's a way to say, well, if this is what the average was and this is what the standard deviation was, we can actually predict what different percentages of the population could do. So let's say we had 55 people come into our lab and we had them do bench presses and we figured out their maximum bench press strength. I think these range from about 140 something to 203. So the easiest way to understand this would be to rank these from the lowest to the highest. So here would be someone down around 145 bench press, and here would be someone up around 205. And in what we call a normal distribution, this is what the rank would typically look like. A lot of people would be clustered around the mean, which is 167 or so pounds, with a plus or minus 11.4. So the range is from 145 to 205. But the standard deviation, which is sort of the average distance each of these values are away from the mean, a positive or negative, is 11.4. And that 11.4 becomes important because it can help us predict, for example, what 75% of people could do. And that's typically what we're trying to do in the workplace. So basically, half the people could do more than 167 and half the people could do less. But if I wanted to say, well, how far do I have to lower this bar so that 75% of the people would be capable of it? We can do that just by hand here, and in fact, I'll show you that here. So we have what we would call the 25th percentile value, or the value that would be acceptable to 75%. And basically what I could see is that 41 into 55 is about 75%, and 41 of the 55 observations are above, and 14 of the observations are below. So this would kind of be the value here, around 159, that if I set the bar at that 75% of the people would be capable of this. In a normal distribution, which this looks like, this might be a little bit of an outlier. In a normal distribution, that actually ends up being very easy to calculate. It's typically the mean minus 2/3 of a standard deviation. So for example, in this case, the mean is 167 or so, and we found that 159 was where we'd have to set the bar for a 25th percentile. That ends up being 7.9 centimeters below the mean. And 7.9 is about 67%. 7.9 is about 2/3 of the standard deviation here. And that's typically in a normal distribution what we find. So if we want to find out what 75% can do, we would take the mean and subtract 2/3 of the standard deviation. And then for those of you that have done this in stats, that would mean a z-score of minus 0.67. But very simply, it's you find out whether you have a normal distribution. If you do, then you take the mean minus 2/3 of a standard deviation, and that gives you a pretty good idea of what 75% of the population could do. Typically designed for males or females, because on average, females would be the limiting factor. So the 3D static program looks like this, and this is typically the kind of thing that people use. Maybe they use Jack if they are fortunate enough to have that software. It uses very similar equations to 3D SSPP. You can manipulate this mannequin into various postures. You can apply loads down in this case to either hand, and you can define how much those loads are. You can define where the hands are, so it can predict what a person would do, and you could tweak that afterwards. So typically, from the perspective of today's talk with the shoulder and elbow, let's say, you can actually get from the table that gets output, you get an idea, for example, in this particular posture here, that the elbow for that exact elbow angle might have a strength of 31. So these values all represent what the strength would be on the left side. Of course, there's only one side to the trunk, so there's no corresponding right values. So in that posture, we might predict that the left elbow could produce 31 Newton meters, and the right could produce 34. What a lot of people don't realize is that in 3D static, the right hand values are higher than the left. They assume that the model is right hand dominant, and they assume that all of these joints are 90% of those joints. So if we have a moment of 17 Newton meters, that is substantially less than what the average person could do. So you would expect that higher than 50% of the population could do that. And in fact, the software will go in and calculate that for you. That's why it's the 3D static strength prediction model. It predicts what percentage of the population would be capable of this. In this particular example, we would have, if the moment was 210, it actually, and I've set this up on purpose, it would actually show that 75% would be capable of that, because 2010 is more or less the mean minus 2/3 of the standard deviation. So what it does is give you the demands in blue here and the capacity, which are estimated from the equations for that specific posture. So here we could say, for example, of an 8 Newton meter moment, when the strength is 10 times that, we'd predict that 99% would be capable of that. Whereas if the moment is 39 Newton meters and the actual demand or the strength is 39 Newton meters, then about 50% could do that. There's a little bit of decimal places here that are being left out. And this just illustrates the example I gave, where 210 is equal to 275 minus 0.67 times the standard deviation. So under the hood, the software is doing all of this for you. And most people, when they're trying to determine the strength capacity, and this is for single efforts, this is for maximum single efforts, most times when they're trying to do that, they would use a software package like this, which does most of the calculations for you. You would put the mannequin in a posture. Based on that posture, it would determine what the strengths would be. It would also, based on the hand loads and the body mass, it would determine what the moments are, and then it would figure out where you would be on some distribution. And typically when we design tasks, we want to make sure that none of these values are less than 75% capable for females. And in this case, we can see the hip extensor demand and even the shoulder abduction moment on the right-hand side and the left-hand side would violate that, and we would have to deem this task to be unacceptable. Just to indicate, there's other ways to do this. We've been working for years on trying to estimate arm strengths in various directions based on where the hand is located and not based on all of these postures, which a lot of times this software can be used to kind of get the answers that you want. So we've had a long program of research which we're continuing where we put the hands in various locations, measure strengths in 26 different directions, and we're in the process of developing regression equations which seem to be working quite well. And really all they need to know is the vertical height, the reach, and the lateral displacement of the shoulder relative to this. So it would be how far forward, how far lateral, and how far above or below the shoulder. So this is a simple method which seems to actually be working quite well. and we're going to be continuing to develop that. So the point is that there are methods out there to predict maximum strength at the shoulder for the very specific conditions that you might be testing. Now, how do we do this at the hand, wrist, and forearms? Well, basically, this typically isn't in software. 3D Static does include a wrist now. I'll show you some of that data, but it doesn't really even have a hand. It has no idea what the grip strengths would be or the pinch strengths would be. And that's some of the research that I'm going to show you right now that's been incorporated in my handpack software. So there are some resources out there. An excellent resource for various strengths is by Peoples and Norris in 2003. I believe this was done to help designers in England determine, what the torque should be on pickle jars or doorknobs for various ages and populations. This has just got a ton of data for practitioners to make at least good estimates of what the strengths might be for given conditions. So, for example, they had various hand grip dynamometers with different apertures. They had people open and close against resistance, and they could measure the maximum torques with different interfaces, butterfly nuts. They simulated jars where they could measure maximum torques. So just to give you an idea of what was done in the study, and it's really a worthwhile reference to get, one of the advantages of this is that they did ages 2 to 5 right up to 81 to 90. So it gives us a good idea of how strength decreases with age. That becomes increasingly important without things like mandatory retirement ages. We're getting an older workforce, as well as the fact that people are living longer. And also the baby boom generation is moving into that more elderly, into those elderly age groups. It's important to know how the predominant number of people in your workplace, how that strength changes. It's got separate data for males and females. It's got things like pushes with the fingers and the thumbs up and down, pushes on cylindrical handles and pulling on those handles, pulling with different kinds of grips on leather strips, on blocks of different apertures, different one and two-handed grips, twisting things like doorknobs and levers and butterfly nuts, and also opening things. And again, I think a lot of this was originally intended to help design products for consumers, but can be used very nicely in the workplace as well. Here's what a typical table looks like. You get, for example, at the 31 to 50 age group, you get male and female. They show how many subjects they measured. Here would be the maximum pushing force, for example, for females, 131.3.5, and just as importantly, what their standard deviation is, so that you could then subtract 2/3 of this, let's say about 20 from 133, and estimate that 75% of females could push with their thumb, with 120 or so newtons. That number might be different if it was forwards or downwards. There's also a good resource of information by Maitel and Kumar from 1998. And they've taken guidelines for the practitioners in the International Journal of Industrial Ergonomics and provided many, many tables that they've culled from various research as a lookup for practitioners. In addition, Richard Wells and Grieg have determined various strengths in an excellent study, which was a part of Grieg's master's thesis. So they have male and female data for power grasp, lateral pinches, and pulp pinches. And then they have them being exerted in various directions as well. Grips, pushes, pulls with these different grips. So this is very valuable information. Again, means are given with standard deviations and the number of subjects. So the practitioner can go to tables like this, pull out information like this, and start to at least make guesses. These are torques as well. The flexor, extensor, pronation, supination, radial ulnar deviation in the same grips. Start to use this data to try to make some estimates in cases where, there's not often going to be a study done on the exact task that you're looking at. You've got to go to data like this to make your best guesses. So these next couple tables are going to be quite busy. I just want to give you a general idea of how much data is out there. This is more or less the data that I've included in my handpack software. So for example, for wrist extension, for pinch grips, there are a couple different studies that I could use to average. And here you see I've sort of blocked out the numbers, but here you see the coefficients of variation. For power grips, you can average across a number of studies. So what I've tried to do is go into the literature over the years, determine which research is worth including and which research might have had issues or have inconsistent results, and try to summarize that for different, for example, for hand grips, pinches with lateral grips, pulp pinches. There's a wealth of information out there. Now, you guys don't necessarily have the time to go and read the literature and figure out what's good and bad. So that's what I've tried to do in the handpack software, and for practitioners to have sort of data that they can trust from good sources, and where there's multiple sources, try to sort of have a weighted average of that. And here's, for example, pushing when the fingertip from some data that we have, or pushing with an oblique grasp, or pushing with the thumb pad, just sort of culminating all of the research that's out there. And the point I'm trying to make on these 3 slides is that there is a lot of data for practitioners to use. You don't always have the availability of that data in the literature because you may not have access to online subscriptions. So I've tried to sort of, and others have tried to summarize this in software packages that will kind of do everything for you. So for example, just to give you an idea of what the variability is in some of this data, here would be the 6 studies that I would trust for females in terms of power grip strength, ranked from the lowest to the highest. Some of the work by Sorello et al. At Liberty Mutual, some of the data from Peebles and Norris that I showed you. You can see the range, not a huge range between these, and then the corresponding male data. There's a bit more range in the male data, and on average, males are 61% higher for power grip. If we look, for example, at some of the pinches, and again, you don't need to worry too much about the numbers, but for example, if we rank from the highest to lowest pinch grip strengths for females, you get a sense of how much higher on average it is for males, about 47%. You can see that lateral pinches and chuck pinches have similar strengths. I believe this is mainly because with the 2 fingers up here, the thumb is the limiting factor, and with all of the fingers on the side, the thumb is the limiting factor, and it's really a very similar task for the thumb, both of these, so it makes sense that the strengths would be similar. For things like pinches with 1 finger or with the tip, you can see that the strengths are lower than they would be with lateral grips, and that when you do a tip pinch, you can get lower moment arms about the joints, and you can actually get higher forces. So this is all the data that's available out there in the literature. Again, 3D Static also has some wrist strength data in it now in the new version. And again, you can look at the demand, you can look at the mean. If the demand is greater than the mean, then there would be a very low percentage of the population that would be capable of that. Here's a graph of what the sort of the 3D static outputs look like in the previous version. You can see pronation and supination strengths, how they change with pronation and supination angle. You can see how radial and ulnar deviation strengths change as you become more ulnar and radial deviated. And you can see how wrist flexion and extension strength. So the software is there, and I have some of this as well in my software that is there to sort of help you, given the task characteristics, to determine what the moment demands would be, as well as what the strengths would be. So up to now, I've sort of shown you data that would indicate what the maximum sort of strengths would be. You typically would want to use this if somebody was doing something once a day, or very, very infrequently. And I'll show you that it doesn't need to be very frequently done for the acceptable values to be quite a bit less than maximum strength. But we, have a wealth of data out there that we can turn to at least make estimates and give us a ballpark idea of what grip might be better. Is this one stronger or that one? So lots of data exists out there. But again, if I come back to this curve, that really just tells us what this value would be. What is the maximum that someone could do once? And let's say presumably once a day. And that might give us an idea of acute injuries. But the problem is that most tasks are done repetitively and or prolonged periods of time. And that leads to muscle fatigue and tissue damage. And in those cases, we would not want to recommend that somebody do something at this repetition at that force. That would be a very unacceptable load. So basically, the problem is that it's much easier to do strength tests than it is to do physiological or psychophysical tests. And there's very little data available out there, especially for the upper extremities, related to maximum acceptable forces for submaximal repeated. Excuse me, I just got to get a drink here. Okay, so sorry, I got a little bit of a cold here. Been coughing so much. One of my ribs came out the other day, so I may have to take a drink break every once in a while here. Okay, so when we get to repetitive tasks, we see that the acceptable loads are quite a bit lower. And then the question is, well, how does this curve work? How could we sort of scale a maximum strength to help us estimate what someone could do repetitively? And what is the nature of this curve? And of course, this curve will be different for every body part, but maybe what these are as a percentage of the maximum may be similar for different body parts. Okay, so I don't want to get too much into this, but I do want to talk a little bit about muscle physiology because it becomes very important in understanding how a muscle fatigues and why this curve looks like it does, and why a muscle fatigues at a faster rate the higher the force that you go. So if we look at a muscle, here we see a series of motor units. This motor unit, well, this is one motor unit, and a motor unit in a muscle is a bundle of a series of fibers that all have similar characteristics. We've heard of slow twitch fibers and fast twitch fibers. They'd all be innervated from one nerve, and there's a very orderly recruitment that occurs with these, and that has very important implications for predicting muscle fatigue. So each of these would become a motor unit. There would be a series of motor units in a muscle, and each would be innervated from its own nerve. So if we, for example, look at a cross section of a muscle, you can see that here are bands of motor units, and an action potential would propagate. It'd go into the muscle. It would release calcium, and then each of these fibers would shorten, and in shortening would put tension on a tendon and would apply a force on a bone, and that's how we do work. But the important thing to see here is that these bundles will all be innervated by the same nerve, and each will be sort of activated at the same time. And some bundles are small and very fatigue resistant, and some bundles are large and get recruited last and can generate a lot of force, but will fatigue very quickly. So every time a muscle gets an action potential, a motor unit, you get a single unit of force, which is a twitch. All of these fibers were shortened simultaneously. If you have a number of fibers that are firing, all of these twitches will add up to generate the force. The twitch occurs in about 100 milliseconds. You get a rapid buildup of force and then a relaxation period. But the part I want to show you, which has implications for fatigue, is related to the size principle, which was discovered by Elwood Henneman and in sort of the late 50s, early 60s. And I just want to quickly go through this because you all probably have heard the term slow twitch and fast twitch, and sprinters are fast twitch athletes, and long distance runners are slow twitch. So basically what happens is if you activate a muscle, you send some juice down to a muscle from, let's say, 0 to 100%. What happens is the slow twitch fibers have the smallest axons, and they actually depolarize first. They tend to have small fibers. These fibers tend to produce fairly small forces each time, and if you keep stimulating the muscle, it'll continue to have twitches. So that twitch that I showed previously, you can kind of see one of those shapes here. Slow twitch fibers have very low forces produced by the twitches. They tend to take a longer time. But the nice thing about them is these low forces here, which kind of represent this, you can do them for tens of minutes and even beyond an hour, and those muscles can still be generating the same amount of force. And if we define fatigue as sort of a drop in force generating capacity, these slow oxidative units, and they're oxidative because they're constantly using oxygen as a supply, and it's in constant supply to the muscle, they can pretty much not go indefinitely, but they can go for a long time. As you turn the juice up to the muscle, this axon will be stimulated. It will produce more force, and it may be able to maintain that force for 2 or 3 minutes. It has higher twitch forces, but eventually after about 4 minutes, its force will drop off. And after 60 minutes, there'll be a fairly large drop off in its force. So it's good that we don't bring them in right away because they tend to fatigue faster. And then as you get up near 50, 60%, these fibers will all start to fire more frequently, and you'll now activate the fast twitch fibers. And their advantage is they produce a huge amount of force. each time they have a twitch. But their disadvantage is in within seconds, they start to drop out. And after 2 minutes, they're almost producing no force at all. So the beauty of this design is that you can just send one stimulation to a muscle, and it sort of just by physical properties will decide to use the slow twitch. And so they're sort of like this, they call these the Cinderella fibers because she was the first one up in the morning and the last one to go to bed. And if you were to ramp a contraction from 0 to 100 and back down, those slow twitch would be the first ones on and the last ones off. In the middle range, these would be on and turn on and off second. And these would only be on at the end as you did very maximum efforts, but the problem is you can only do those efforts very infrequently. And this is why maximum strength data doesn't help us too much with repetitive tasks, because what you could do once actually decreases very quickly if you try to do it more often than once, even more often than once a day. And so I want to talk a bit about, well, maybe I'll stop right there. I don't know if there's any questions at this point. Not sure. Margot, do you got any questions for me?
Nope.
Okay. Oh, I can hear you.
No.
Okay.
Can you hear me now?
Yeah.
Perfect. So I'll interrupt you if there's questions that come up.
Okay, great. Yeah, so I see some of the questions there. I will provide sort of a version of most of these slides and then a reference list for things that are relevant, like the Peebles and that. I can even provide a copy of some of those papers. But so anyways, this is sort of how muscles work, and it has implications for fatigue. So obviously, if we're looking at doing things repetitively and we know that they can't be done at 100%, this has something to do with muscle fatigue. So I just want to make sure we're all on the same page in terms of what the definition of fatigue is, or at least how I consider fatigue. And it's ANOCA has defined it as an exercise, but you could also say work-induced reduction in the ability of a muscle to produce force or power, whether or not the task can be sustained. So for example, if I asked you to hold a 10-pound weight with your elbow flexed in front of you, you would start to fatigue immediately. It doesn't mean that you would stop doing the task immediately. It may take 2 minutes or a minute before you couldn't do the task anymore. But the instant that you couldn't do the task isn't the instant of fatigue. The instant of fatigue starts almost immediately because, as you saw, especially at the higher level contractions, those larger fibers will become fatigued almost immediately. And so you have almost an instant onset. So there have been a few methods. Some of you may be familiar with Romert's method to try to determine, for example, if somebody held a 40% contraction for 10 seconds, try to determine how much rest they would need. Now, that's nice because it gets away from assuming you can do maximum efforts indefinitely. The problem with it, though, is that it's very rare that we do things in the workplace where you're off for a certain amount of time and you're on at 40%, and you're off and then you're on at 40%. For tasks that are like that, then this method can be used. I'm not necessarily going to teach you the method. I'll just give you an idea of how it works. I think that the method that I'm going to present you at the end is probably a better way to go for this. But many people have used this method in the past, and I just wanted to sort of address it. The first thing that we need to know is, if somebody had to hold something to exhaustion, how long could they go? So for example, that example I gave you, let's say that 10%, the 10 pounds with your elbow bent 90 degrees with a barbell in it, let's say that was 30% of your maximum. The first thing to do would be determine, well, how long could you do that? Now, it's not very often that we do things in work where we go to exhaustion and then try to recover. But this actually becomes an important element in trying to determine things like rest allowance. So there are some methods. I'll show you just a graph. I'll come back to this in a second. There are many different curves out there for different body parts and from different research efforts. And you can see here that, like the curve I showed you before, if your effort is only 10% of maximum, you could sustain that for a long period of time. And if you're doing it at 90% of maximum, then it would be a very short amount of time because of those fast twitch fibers. And 100% you can only do for a couple seconds. So this red curve and the blue curve are sort of shown in these equations. This would be the amount of time you could hold something. This would be e to the 60.27 minus the relative force. So relative force would be force as a percentage of maximum. Is it 20%? Is it 30% divided by 2.2? This equation here is a little bit different in that it includes the relative force, but this considers max to be 1, so 0 to 1. It has it squared and it has it cubed. And there's a couple things about this equation which become important. Is one of the issues that there is when using the Romert equation is it assumes that you could do anything below 15% of maximum. It assumes you could do for an infinite amount of time. Now, if I was to ask you to put your arm out in front of you and we were to calculate what percentage of maximum that would be, it probably for most people close to 15%. And I guarantee you after about 4 or 5 minutes, your arm would be shaking and you couldn't do that anymore. So we know that this equation is probably not correct at the low levels, even moderate levels. But it does bring in some of the concepts of fatigue. So what these curves are showing is sort of how quickly fatigue occurs at different percentages of maximum. So if you think of this as being sort of 0 and 10% fatigued, you think of this as this value goes up on the y-axis, that means you're becoming more fatigued. And let's say we're going to say, well, you want to be 10 units of fatigue or 10% fatigue or a 10% drop in strength. What you see is that you get to that same level quicker if you versus this is a 20% effort, it would take about 1.5 minutes to lose about 10% of your strength. Where because you're bringing in more of those more fatigable fibers as you increase the force to 30%, it would only take 0.66% percent of a minute, 40 seconds or so. And then if you went up even more to 40% of maximum, now you're starting to almost get all of those fast twitch fibers in. And because they're so fatigable, you can see the slope of this curve goes up. And in fact, you would lose 10% of strength in about half of a minute. And so the point I'm trying to make is that the rate of fatigue, the rate that you would lose 10% of strength, actually is quite a bit higher as you progressively increase the force demands. And that is because of that physiology I showed you, where all motor units are not created the same. As you increase the force, you bring in stronger units, but you also bring in more fatigable units that fatigue at a faster rate. So when we design jobs in the workplace, we sort of want to abide by this curve. So for example, if I had you in a flexed position for some period of time, let's say sorting mail, what would happen over that period of time was that you would accumulate more and more fatigue, and then I would need to provide you with enough rest where you would relax and recover over that period of time. These two might not be necessarily the same. But the more fatigued you become, the longer time you need to recover. And if this is sort of fatigue accumulating, let's say over a day, then you're going to need enough time to recover. If you don't fully recover, then you're going to be even more fatigued at the end of the next day, and you're going to either need a weekend or something to recover from that residual fatigue, let's say after 5 days. If you're doing dynamic work, you get sort of recovery and you get fatigue and recovery, and you get a ratcheting up of fatigue, let's say over a shift as you do repetitive tasks, let's say on an assembly line. This is you working for 30 seconds and recovering for 30, and the recovery is not quite enough time because of the rate that the fatigue is accumulating. Then you may need, a 16-hour break after work to recover before you start that next work day. So just quickly, the way that the Romert rest allowance calculation works is it sort of is this demand and capacity, and it works sort of in two ways. One is you need to know what is the demand on a joint, like so for example, what moment is at the shoulder versus the capacity of that joint. So here would be a strength curve for the knee, similar to some of those curves that I showed you. And so you'd want to know what is the joint moment as a percentage of the strength. Is it 50%? Is it 40%? And the reason this 0.15 is in there is basically your rest allowance. You don't need rest allowance if this joint moment is less than 15% of the maximum strength. This becomes a complex number and the equation doesn't hold. So really this equation only says you need rest if your joint moment is more than 15% of your strength. It also has sort of a demand and capacity in terms of endurance. So, you could measure how long somebody is holding something. For example, in this case, is it 0.66 minutes? Is it 1.55? So this would be the joint moment over the demand would be 20%, 30%, and 40%. And in this case, the holding time would be 1.55, 0.66, and 0.45. And those would be the parts that would go into the equation. So maybe 0.2 and 1.55 would go here. And then you'd put and so the only other thing you'd have to know is endurance time, and that comes from that equation I showed you. So maybe at 40%, you might estimate that people could do 2% or 2-minute maximum hold. So how large is the moment on the joint relative to its strength? and how long is the holding time relative to its maximum endurance time. So that's these two teeter-totters that occur here. And what I want to show you is basically what these equations look like. So for example, you can only do 100% contraction for about 6 seconds, whereas you could do an 80% contraction for, zero point 0.4 minutes. And what this shows is how much rest you would need. And you see that the need for rest goes up. So the need for rest kind of goes up gradually at 30%. It goes up much more severely at 50%, and even more so at 80%, and even more so at 100%. So for example, if you held a 50% contraction for zero point 0.6 minutes, so 33 seconds, this would say that you would need almost 3 minutes to recover. And so again, to go back to this, if you held, for example, here it shows if you hold a 30% contraction for 0.66 minutes, you would need 0.72 minutes to recover. Here the curve shows if you hold a 30% contraction for 0.66 minutes, you need about 0.76 minutes to recover. So what I'm trying to show you is not necessarily how to necessarily use this method, because I think there are other methods out there, but this curve nicely shows that the rate of fatigue goes up as you increase the load on a muscle, that you can only do maximum contractions for about six seconds or so, and even then you'd need 2 minutes to recover. And so we'd like to balance jobs out that are heavier, where they have recovery interspersed, as opposed to having them done sequentially, because you'll need much more recovery at the end. So there are some methods out there that can be based on strength and demands in terms of trying to estimate for a given holding time how much the rest would need to be. But that relies on the job being very stereotypical, always being 30%, always being for a certain amount of time, and always getting a certain amount of recovery. Now, there are some psychophysical studies that have been done, much like the Snook tables that were done for lifting and lowering, pushing, pulling, and carrying. In fact, much of the best research was done by Snook and his colleague Sorello at Liberty Mutual. And those are nice because they actually do very specific tasks and give you an idea of what would be acceptable for that task, for that repetition, for that demand. So let's just talk a second about psychophysics and sort of its history in ergonomics. The power law in psychophysics was first developed by Stevens. And what he sort of discovered was, if you were, and the psycho part would be your perception, and the physics would be the real stimulus. So here we see a real stimulus. Maybe you're presented with a brightness that increases from 0 to 100 units. And this would be how you would rate that brightness on a scale, let's say, from 0 to 100. So what we see is we're very sensitive to light at very low stimulus intensities, and then we become much less, as it goes from 50 to 60 to 70, we become much less. Whereas if you were to give someone an electric shock, they'd be very sort of the stimulus, they wouldn't sense much, and then there'd be sort of an exponential increase. And what we found is every different sensation has a different nature of a curb, and you can define that nature with an equation. But what Snook first wanted to do, and Snook and Irvine in 1967 is the first psychophysical study I've ever found on physical ergonomics. They said, well, maybe people can actually judge what's acceptable to them for manual materials handling tasks. And they said, if we give them training, they are able to, for example, do repetitive load lifting from floor to table height. We tell them what frequency. They could actually tell us what load should be in there so that they could do this for 8 hours a day. And you need to bring them back multiple days so they can go, okay, my back hurts because I did too much. So the next day they do a little bit less. And so over the years, all of that data was compiled into what are the Snook and Sorello tables, or the Liberty Mutual tables for lifting and lowering. And then Snook and his colleagues began to do psychophysical studies of the upper extremities in 1995. And I'll summarize some of the upper extremity psychophysical studies that have been done. And so typically what they do in these studies is they'll have someone, for example, doing a repetitive wrist extension task. The subject will be in control of how much torque it takes, or if it's a pushing task, how much force it takes. They'd be trained to do this at a particular frequency. They'd be given normal workday rest, and they would come in for weeks and weeks and do this task so that they could eventually determine what would be acceptable. So they have a controlled repetition rate. They're instructed on what the task would be, a screw driving task, gripping task. The subject would control the amount of resistance through an unmarked dial, so that it's not like they could set it to the same thing every so often. Every 15 minutes or so, the experimenters would either increase the resistance or decrease the resistance to force the subject to come back to see how reliable they were at coming back to what was acceptable. And you can see the instructions they were given in, work as hard as you would as if you're on a piecework or incentive basis, getting paid on, like again, on piecework, but you won't want to have any unusual discomfort or fatigue in the hands, wrists, or forearms. They also monitored symptoms and heart rate and things like that, just to make sure that subjects were doing this accurately. Subjects were typically trained for at least 4 to 5 days, ramping up to 2 to 7 hours. And they would then do testing over another 3 weeks. So they'd give training and then they'd kind of do the testing to determine these maximum acceptable values. The advantage is, in addition to asking people what they could do maximally, they also tried to use psychophysics to determine what they could do repetitively. So what are some examples? The first one was in 95 that looked at repetitive wrist flexion with power grips here, and pinch grips, and also wrist extension. So the subject could again control how much resistance was there. They also did maximum acceptable forces for radial and ulnar deviation. This particular study was ulnar deviation, so going this way with a power grip in 97. They did maximum acceptable repetitive wrist extension with a pinch grip, so it looked like this. So they sort of repeated that study. Here you can see a number of subjects in a work cell doing these training studies. Sorello did a number of different tasks, so pronation and supination with different screwdriver handles, with different yokes, did maximum hand grips, and ulnar deviation with power grips. And they did these at various frequencies. They tended to do these studies at quite high frequencies, 20, 25, 15 times a minute. And I'll show you a summary of all this data later. There's also a very good study done by Anne Moore as part of her PhD with Richard Wells at the University of Waterloo. This was a wrist extension task. So basically, the subject would hold on to this. They could generate a certain torque that would tend to flex their wrist this way. So this object was turning this way. You could set the maximum torque on it so that once you gripped it, you would have to generate an extensor torque to stop it. And so they were interested for various combinations of frequencies and durations, what people found to be the torques that were found acceptable for example, doing this 6 times a minute at 5 seconds each, which would be a duty cycle of 30%. And so they got some very good data, some of the only data actually for duty cycles above 50% of maximum. So I've been doing research with Ford for about 16 years or so. And typically at the beginning, Ford would say to me, my colleague there, Allison Stevens, would say, there's data out there, there's some strength data, but there's some real specific things we do very, very often when we build cars, like hand impacts on trim, putting electrical connectors together with various grips, pulp pinches, finger presses. Inserting hoses, I'll show you some videos of that, thumb insertions, finger pulls, hand starting. If you have, let's say, a machined part that's very large and expensive and you're going to have to put a few fasteners into it, if you put the fastener in with a handgun on the wrong angle, it'll strip the fastener and basically have to scrap the part. So they will typically put these in, get the fastener started through 2 revolutions. So it's a lot of repetitive hand motions. I've talked a little bit already about some of the arm strength work we've done. I'll go in more detail on the things in blue here. Once we compiled all of this data, it went into this handpack software in addition to all that other data from other studies that I showed you. We've also done some work on transducerized DC tools versus air tools. We did a large validation of the ACGI HTLV when it first came out. And more recently, we're doing a lot of work, not just with Ford, but also Chrysler and GM as part of the U.S. car group in the U.S. and with some funding from the Automotive Partnership Canada and NSERC, trying to improve work simulation, digital human modeling, the use of virtual reality, that kind of thing. But really what I want to talk about today is some of the psychophysical studies that we did that are similar nature to the ones I just showed you by the Liberty Mutual folks. And So you probably can hear that, but you can't hear me otherwise. Um, just Let me just stop this here. So here you can see somebody putting electrical connectors on with many different grips and many different orientations. They're doing it very quickly at very high rates. Now I'm going to pause that just because. So we did a very large study where we had subjects come in. We trained them for 27 hours with different connector interfaces and different postures. I'll show you those in a sec. And in each case, we would always measure what they could do maximally, and then we'd ask them at different frequencies for them to tell us what they could do repetitively. So in this particular study, we had 24 females, and because we wanted this data to be applicable to the workplace, we, instead of most university research, at least in kinesiology, that gets done with college age students, we had an equal number of people in groups ranging from 20 to 59. We had people give us rate acceptable values for 2, 7, and 12 a minute because this task tends to be done fairly repetitively. We had them do it with 3 different grips, which I'll show you and describe in a second, and also 3 different postures. We would have them tell us what their maximum force was, what I'll call a maximum voluntary contraction, in addition to what we would call the maximum acceptable force for that task. And we were trying to simulate tasks like this. So here you can see, for example, somebody with a pulp pinch with the index finger and thumb in a neutral posture, ulnar deviated, and an extended wrist. Quite often, there's very little clearance for parts to be pushed on, so people would do this with a fingertip or a finger pad. So we did that with neutral, ulnar deviated, and wrist extended. And then an oblique grasp was sort of like a power grip with your thumb out front. This could represent somebody putting a hose on, but also a bundle of wires. So we did this again, neutral, ulnar deviated, and extended. To do this kind of research, you need a simulation device similar to the one that would have been used in Snook. Just quickly, all the subject saw was this wooden piece or the dowel and an unmarked dial. The rest of it would be covered in a wood box. But basically, the subject would push on this, it would compress the spring. We'd measure the force on a force gauge. If the subject felt that they could do more, they'd turn this dial, it would move this piece closer, preloading the spring at a higher force. They push it again, they say, okay, that's too hard, and they could loosen it up. And every 15 minutes, we'd sort of try to mess them up a bit by making it harder or easier in the hopes that they would reliably come back to the same values. So for example, in one of the conditions where they did finger presses for 7 per minute, these would be the time histories of the forces we would record. If we took the peak force from each of these, and I'll just focus on the peak force for today, we might find that on average, the average force was 8.5 pounds and the standard deviation was 0.7. So then we could figure out what an individual subject found acceptable for that task, but then we could also average across all of our subjects to see what that distribution looked like. We also determined sort of what the duration of these efforts were, and this will become important later when I talk about the equation I developed. Obviously, if we assume a 40 Newton force, let's say here, we'd want to kind of make an estimate of how long that force would be exerted. So really all we did was we said, okay, well, what rectangle with a height of 40 Newtons, how long would that rectangle have to be? So the area under this yellow curve would be the same as the area under this blue curve. I don't want to spend too much time on this, but what we found was on average, we would sort of estimate that the equivalent of 40 newtons would be applied for about 160 milliseconds. In this exact example, it was 0.11. So here's what these peaks would look like. So if I plotted these peaks out over time instead of all on top of each other, this is what a testing session would look like at the end of the 27 hours. This is for oblique grasp being done 12 a minute. So maybe we had set it very low at the beginning and the subjects would say, oh, we could do more than that. And over a while, they kind of settled into a force that they thought was acceptable. And you can see there's some variability on this. And then maybe we set it lower and then they kind of crank it up and overshoot and they kind of settle back. And then we set it lower again and they overshoot and they come along. There should be another line here. Maybe we set it very high this time and they kind of came back. And we wanted to make sure they kept coming back to similar levels, which in this case they were. And then in the last 15 minutes, we'd say, okay, well, for this condition, for that subject, you would tell us that the acceptable force is 12.6 pounds. Sorry, this is an old Ford US graph, but 12.6 pounds with a standard deviation of 1. And then we could average that across all of the subjects. And so what we found in that particular test was that, as we expected, the acceptable forces dropped with frequency. You would expect that, as some of those curves I showed you. That when pushing with an oblique grasp, they found higher acceptable forces than the similar forces they got with a pulp pinch and a finger press. And basically, we see the reduction with force. We could also normalize these to 100% to see how they change. For example, at 2 a minute compared to if they just did one single effort. So I'm going to show you a video in the next slide for a couple seconds. It might be a little loud, but I can try to turn it down. And basically, it's from a study I did with Dave Andrews when I was at the University of Windsor, and it's related to hose insertion. So I'll just show you for a second what it looks like when people are putting hoses on in the workplace. Rocking out there too. Okay, so basically in the automotive industry, hundreds of hoses are inserted. The problem with hoses is that they need to be easy to go on, but once you turn the engine on, they can't just blow off. So they're kind of a unique challenge, and they can be put on in pretty much every posture you could imagine. So similar, we simulated hose insertions. They tend to be longer efforts that are done less frequently. We gave subjects 18 hours of training before we did a data collection similar to the one I just showed you. And a lot of grad students helped out with this study as well. Um, and so here you can see more static photos of people. They have different sized hoses. They get in different postures. We used 15 female subjects in the same range. We looked at a lower frequency because these efforts, instead of being around 160 milliseconds, tend to be more like 750 milliseconds. I'll show you the 5 postures that we tested to see if there was any kind of theme that we could develop. And then also in each of those postures, they would give us an idea of what their maximum strength was, and then they would tell us what was acceptable. For example, at 3 a minute in a particular posture. So we simulated people sort of reaching over a fender and pushing a hose on medially, and with a longer reach, pushing down, pushing forward, and then reaching forward and pulling backwards. So we had 3 very different tasks with different moment arms, different force directions, different muscle groups being used. By no means did this represent all the postures that people get into, but we were sort of hoping there would be some common things that actually did turn out in the study. So what we see is that the acceptable forces drop as you go from 1 to 3 to 5. So that gives us an idea. We see that when they were pulling and they were pushing down, so pulling here and pushing down, that's where the highest acceptable forces were, but that's also where the highest strengths were. You could imagine that when you're reaching at a long distance, you're gonna find lower forces acceptable than when you can get the load nice and close to you. So the problem is all of these were very different, and they only represented 5 of the many tasks that could be done. So then what we did was we said, okay, well, let's take these values and divide them by the maximum strengths that we measured in these subjects. And what you see in this next graph is a very nice common theme that came out. So if we sort of back calculated what it would have been in the connector study at 1 a minute and what it was in those 5 hand positions, even though each of these values are different in terms of pounds, they all ended up being a very similar percentage of maximum at 1 a minute. And it ended up ranging between about 62 and 68, on average about 65%. So basically what this is saying is that if you do an effort for 750 milliseconds once a minute, you should only be doing about 65% of your maximum. And this came as a bit of a shock to the people at Ford because basically they make a car every minute. So even if they do one part on that car every minute, now instead of using the strength values from 3D static or from whatever data they might pull out, now they can only use 65% of that. But that culture has changed and the designs have changed with it. And I'll show you sort of how I developed an equation to determine maybe what this percentage might be at 4 a minute or 8 a minute, also related to duty cycle. The other thing I used to sort of convince them that this isn't so unreasonable is if you look at the frequency correction in, this is a bit of a rough version of it, but in the NIOSH lifting table, you see at frequencies of 1 a minute, they correct for a 75% correction factor. And if you look at the ACGIH TLV for hand activity level, they would suggest at the lowest hand activity levels that you not exceed about 7 out of 10 in terms of effort. So this is consistent with what's been shown in the literature previously. So now what I want to do is show you how I've taken all of the data from those studies that I've shown you, the Snook and Sorello studies for the upper extremities, the study by Ann Moore, and some of our own studies with myself and my colleague Dave Andrews, and recently published a paper called Predicting Maximum Acceptable Efforts for Repetitive Tasks. And this equation is based on duty cycle, not just frequency. Now, this is kind of a new term, maximum acceptable efforts. And what it means is, and this effort is an effort as a percentage of maximum. So, for example, in this particular case, for this particular task, the maximum acceptable effort would be 64% of maximum strength. And it's basically the maximum acceptable force or torque or moment as a percentage of the maximum strength. So what I wanted to do was pull out the best of the psychophysical studies, and I've shown you the ones that sort of made the cut. And there were some things that needed to be there for inclusion. First of all, I was mainly interested in people doing things with the upper extremities, but not there's some data out there on using power tools and things like that. I wanted to keep it to grips and pushes. The study had to be based on what could be done for 8 hours. People needed to be trained over multiple days. There's some experiments that have been done where you come in, you try the task out for a while, and then they ask you what your maximum acceptable forces are. You might give a value, go home that night, wake up the next morning and be very sore and go, geez, I really overdid it. Or you may not be trained enough to do it as high as you will in a couple weeks if you get training. So we required that there needed to be training over multiple days, that only one task be tested on any particular testing day, that subjects be given at least 40 minutes. There's some data to show that you need to give them at least 40 minutes to try the task out and make adjustments. And that I also, because I wanted to base this on duty cycles, that they needed to give me some idea of the durations. Now, just let me define what I mean by duty cycle. Let's say a muscle or a joint or a hand grip is done at 30% of maximum. And let's say, for example, it is done, it's on, off, on, off. This is the kind of task we could analyze in Romer. We could say, okay, if this is done for 6 seconds at 30%, would 6 seconds rest be sufficient? And if not, there would need to be more rest or a lower effort or a lower duration. So duty cycle is, this blue area is the work time and the white gaps is the rest time. And so what is the work time as a percentage of the total time that this is being done? For example, in this case, it's 1 minute. So just to give you an example here, if this is 6 seconds on and 6 seconds off, and that cycle is done 5 times a minute, then the muscle would be on for 30 seconds and it would be off for 30 seconds. So the total time is 60. This would have a frequency of 1, 2, 3, 4, 5 per minute and a duty cycle of 0.5 or 50%. Here would be a task that is being done 1 second on, 1 second off, 15 cycles a minute. That would still turn out to be 30 seconds on and 30 seconds off. So the duty cycle would still be 0.5, but the frequency would be 15. So the question is this more fatiguing than this is? Because they're both on at 50%. What's more important, to know the frequency, to know the number of rests, or is it maybe just important to know what the duty cycle is? Would these tasks have similar fatigue rates? So this is just a quick summary, just to give you an idea of the different kinds of tasks. So I've shown you the Snook studies, the Moore study, my connector study, and the Andrews study. The number of subjects, these are the range of frequencies. So you could see the Snook stuff was done all the way up to 20, 15, 20, 25, 15, 20. Most of their studies tended to be done at the high frequency ranges. Ours tended to be done at the lower frequency ranges and something intermediate here with the Moore study. They did various wrist flexion, extension tasks, ulnar deviation, supination, pronation, a wrist extension task, pushing with pulp pinches and fingertips, hose insertions. So quite a wide variety of different tasks. If you look at the frequency and the duration of each effort, which is provided, you could calculate that, for example, they did 2 efforts at 0.81 seconds per minute. That was 1.62 seconds per minute. 1.62 divided by 60 is 2.027 or 2.7% of the minute. So you can see here that there are very few tasks that went over. These are the only tasks in the studies that went over 50% duty cycle. I have a PhD student right now that we're going to be doing some psychophysical studies in this range to try to fill this data set out. And our data done at fairly low duty cycles. So just to give you a sense of kind of the variety of frequencies and durations that we looked at, if I take all of these frequencies and plot them against all of these durations, you can see that, everything from very low frequencies up to about 25, and everything from duration efforts that were down at, 160 milliseconds up to 7 seconds. Now, obviously, these values aren't possible within a minute because you couldn't do 7 20-second efforts in a minute. That'd be 140 seconds. So there is a bit of a parabola here. And here you can see, for example, with that data set, so if I blow this part of the curve up with that data set, these yellow would be three different conditions that would have a duty cycle of 10 seconds or 10 into 60, 16%. You could do 2 efforts a minute for 5 seconds. You could do 5 efforts a minute for 2 seconds, or 10 efforts a minute at 1 second. So there's quite a range in this data set of different ways of getting the same duty cycle. And this gets at the point, would I expect different acceptable values for this than I would for this because the frequencies are different, or would I expect them to be similar because the duty cycles are similar? So this is what the data looks like if you take all of the curves from those studies and you plot them out against frequency. And at first this was quite disappointing because I was hoping for a better relationship. Here are the curves that I showed you for our data here for pulp, pinch, and finger press. So you've seen those previously. Here are those 5 curves I showed you for the hose insertion data. And you can see they drop off more steadily. And what I began to realize is that's because these efforts are a lot longer than these are and more fatiguing. Here you can see some of the data from Snook. There's some data from Moore that's more horizontal. But really, you really couldn't predict what the maximum acceptable effort should be based on frequency. So then I decided to go back to that table and say, okay, well, maybe I'm going to plot these acceptable forces against duty cycle instead of frequency, and let's see what it looks like. So that curve actually became this curve when you plot it against duty cycle. And again, duty cycle is how long is the muscle on as a percentage of the time that you're measuring it. And now these same curves all fall into line. For example, look at these yellow curves and how different the slopes are. But now when I normalize to time, they both drop at the same rate. You also notice that even at very low duty cycles, people were only doing about 70% of their maximum, which is consistent with what I showed you before. And that this curve now drops more like you would have seen in those curves I showed at the beginning, more at an exponential level. Now the question was, are these accurate? Because they're the only data we have, and what you'll see is subjects probably overestimated what they could do at the very high duty cycles, and we want to collect some more data to sort of figure out what this looks like. So then what I did was if I take all of those points and just make them yellow circles, so get rid of all of the different symbols for the different studies, you get data that looks like this, and I was able to fit a curve to this where I assumed that people could do 100% at a very low duty cycle, in fact, 1 second per day. And just so you know what this is in the equation, if there are 8 hours in a workday times 60 minutes times 60 seconds per minute, there's almost 2,900 seconds in an 8-hour workday. So what I was saying is that if your duty cycle is 1 divided by 29,000 seconds, that you could do 100%, which is why it kind of subtracts that from here. And it drops off very quickly. You can see it just drops like a rock here, drops off very quickly. And then the equation technically goes through 0. Basically, I'm saying there's no force that you want to do 100% of the day. But we really don't have sufficient data to know exactly what happens. So I've sort of stopped the curve at 90%. So this equation explains about 87% of the variance, and there's only about a 7% maximum voluntary effort standard deviation or RMS error. So essentially what the equation does is says if you know your duty cycle, like let's say 0.4, then the maximum acceptable effort would be 1 minus 0.4 minus this very small value to the exponent 0.24. In essence, except for very, very low duty cycles, the equation is essentially 1 minus duty cycle to the exponent 0.24. Now, because I didn't have a lot of data out here to confirm what I had and to see whether or not this really made sense, I went into the physiological literature. Every point on this curve is a study that has shown that when this condition has been done for 1 hour, it resulted in fatigue that could be measured with blood flow, lactate, very detailed physiological measurements. So what this is showing here is that, at around 80%, you would expect that even in 1 hour, these levels would cause fatigue. So because I wanted a curve that was going to be appropriate for 8 hours, it makes sense that it should be substantially less. So I don't have the psychophysical data I have, but at least the curve I have is consistent with curves showing fatigue after 1 hour. And then if you compare this against other methods that might be out there, anybody that's used the Janssen method, if you've gone to Waterloo, you've probably heard of this. The curve is quite consistent with what Janssen would say with his APDFs. It's actually quite a bit more conservative than the ACGIH, which kind of at low hand activity levels would recommend 70% and would drop linearly. It actually turns out that that's probably an overestimation of what people could do. And except for very extreme conditions, I took a condition here where people did 360-second efforts. That was the only case I could get the Romer acceptable values to come anywhere close to my equation. In every other reasonable, it grossly overestimates what people could do. And in fact, assumes that people could do 15% of maximum for a whole day. And you could see there's lots of physiological data to show you don't even want to go over 5%, and it's probably that's even for 1 hour. You can imagine how low it would be if we had data for 8 hours. The other thing I wanted to show you is that for a task that's completely different than this, lifting and lowering and also pushing, pulling, and carrying, if you take the Snook table lifting and lowering data and you normalize the data as a percentage of what people said they could do once a day, and you make some assumptions about how long the lifts took, here is a plot of what those curves do as you go from one lift a day to 10% duty cycle. And if I plot that data against the curve, it's remarkable. If you see that the what's in yellow is what you originally saw, the red is my equation, you see that Snook's lifting and lowering data fits perfectly on this curve. In fact, if I was to determine the best exponent for this particular curve of blue, it also comes out to be 0.24. And if I blow up this 10% part of the curve, you can see that it fills in some of the really low frequency or low duty cycle areas. But it's remarkable that something as different as lifting could end up with similar maximum acceptable load curves as something like a push with a pinch grip or a pronation with a screwdriver. But this data is all falling along the curve. So it does seem that there's some relationship here that might bear paying attention to. So it was the best coefficient for both, and it was obviously the best coefficient when I combined them together. So I want to show you some examples of how you could use data from the literature and 3D static to estimate this maximum acceptable loads based on strength data and this correction equation, which makes corrections based on duty cycle. So if I take a table out of Gregan-Wells and I look at, for example, power gripping for females and males and lateral pinches for females and males, and I try to apply this equation. So let's use an example, and again, these slides will be provided for you, so you don't have to write this stuff down. But let's assume, for example, somebody is doing a power grasp. They're doing 2.3 efforts per minute, and each grasp you somehow estimate from video or something is 0.8 seconds, so maybe 10 frames or so. So then I could say, okay, well, what is the duty cycle? Well, the amount of time you would be engaged in this, for example, power grasp would be 2.3 times 0.8, which would come out to be, 1.7 seconds or something. And if you divided that by 60, then you would be engaged in this for about 3%, 0.03, 3% of a minute. So not for very long at all. So you say, okay, well, if you're doing something for 3% of the time, or 3% of a minute, I don't want to do my maximum 3% of the time because that curve, as I showed you, drops very quickly as you go from a very small duty cycle to something that's even very small as well. I mean, you can see how quickly it drops to 80%, and you're even at 0.2 of a percent. So here we're going to be around 3% duty cycle. We'd expect the equation to come out around 60, 55% of maximum. So if we say that the duty cycle is 3%, then we could say, okay, well, what's the maximum acceptable effort? You could kind of estimate it from the curve. But if I put this 3% in the equation here, I get 0.031 minus a very small value to the exponent 0.24. That comes out to be 0.43. So there's sort of a 43% discount just for doing something 3% of the time. And you would estimate that your maximum effort as a percentage of maximum strength would be 0.567 or 56.7% of maximum. So then you say, well, what's maximum? Well, you go to some data set and you say, well, this is the average maximum for females. So if I was to try to design for 50% of females or 50th percentile, I'd say, well, what is maximum is 162.3. And if I'm doing that for a 3% duty cycle, I'd want to multiply that by 56.7%. And I would say, well, the average person should only do this at 92 newtons. So now I've taken strength data, made some assumptions based on the relationships we've seen in the psychophysical data that does exist and meets the criterion standard. And I'm able to say, make a recommendation for repetitive gripping. Now, it would be great if somebody would go do a repetitive gripping task exactly like the one that I'm interested in and do a giant psychophysical study. But in lieu of that, this would be my best guess. Now, just so you can kind of see an example where, because we typically wouldn't want to design for 50% of females, we'd want to design for 75%. So basically, we'd have a condition where, let's say we use the example of lateral pinch. We'd say, well, the mean value is 64.8. So what the 25th percentile value would be 64.8 minus 2/3 of the standard deviation, which is going to be 64.8 minus 13.2 times 0.67. And so we'd say, well, the strength of a weak female, a 25th percentile female, the maximum single effort strength would be 56 newtons. But of course, if you're going to be doing that for 3.1% of the time, you're going to want to take almost half of that. And so our estimate of the maximum acceptable force, so these are forces here, would be this 56 newtons that a typical weak female could do maximally once, multiplied by this correction factor, and we would set a limit of 31.7 newtons. So in cases where there's data published like Peebles, Mitel, Gregan-Wells, you can go grab that data and you can make these corrections based on this equation. Of course, you need to get an idea of what the frequency is and maybe more challenging what the duration of the efforts are. But you can see that even at very low duty cycles, there's a fairly severe correction that goes on here. So how would we do this, for example, at the shoulder, where we don't necessarily have specific strength data? So let's say somebody's doing a weather strip operation where they're pushing with their thumb and pushing forward with their thumb here. You can use, I'm going to show you an example with 3D SSPP, but I'll go through some examples for 3D static. This is the Ergo solver from 3D SSPP. And for that particular task, it would show that it would solve that the highest force that could be in the left hand would be 91 newtons. And let's say we make some assumptions that this is done, 0.43 times a minute, and each effort is 0.85. So we say, okay, well, what is the duty cycle associated with this? We know that an average person would have a strength of 24.93 Newton meters. But if we take that minus 2/3 of a standard deviation, then we'd say 75% of females, or the 25th percent female, could do about 19.5. And the force that would cause 19.5 is 91 newtons. How do we correct that? How do we determine what could be done at this duty cycle? So just again, one more example. You do 0.43 efforts per minute. Each is at 0.85. So that's only about 0.36 seconds every minute. And in fact, that's 0.006, so less than 1% of a minute this is being done. If I put this into the equation, you can see that even if you just do something, I mean, this is 0.006%. It's about a half of a percent of a minute. You put this in the equation, subtract this small number to go to the exponent 0.24. You find out you get a discount of 29%. So 1 minus that means you can only do 70% of your maximum if the muscle is on for half of a percent of a minute. And so we would then recommend that the task be done at 70.6% of the maximum strength. And so if this is what you could do once, then we could calculate what the percentage of that you could do more often. So we'd want the moment to be 70% of this moment, because this is the maximum strength of a weak female. And so we then want to find what load would result in a moment of 70% of that, which would be 13.75. And I'll just do a couple more examples for you here. Let's say this is the output table from 3D SSPP. You find out the maximum force for the right hand and the left hand. So here you can see we don't want to go over 75% of maximum. I'm just going to focus on the shoulder for this task, sort of ignore some of these values up here. And so we say, okay, let's take a look at the shoulder and try to determine the maximum loads that this person could exert pushing on this weather strip, accounting not just for strength and accounting for being, a weaker 25th percentile female, but also accounting for some sort of frequency. So let's say in the example that we did, let's concentrate on the left for right now and the right. So the once a day maximum moment would be the maximum moment that would be allowed to stay within 75% would be 30.2. If we were designing for 50% of the people, it would be higher, but we're designing for 75%. And the force that caused that was 138 newtons. So I kind of had to play hot, cold with loads until I got this up to 75% capable. On the other side, I wouldn't want the moment to go over 31 Newton meters, even for a single effort. And it took 87 newtons to get that force. So you got to do a little bit of monkeying around with 3D static to get this to work for you, but I'll show you there's a little trick in it if you use this software or software like it. So then I say, okay, well, what is the maximum acceptable moment? We've already decided that for this weather strip task that we don't want to go over 70% of maximum given that very low duty cycle. If we say that the one-time moment is 30 Newton meters, then 70% of that is about 21.3 Newton meters. And same thing over here, 70% of this 31. Again, this is a little bit higher than this because the right arm is in a different posture, but it's also a little bit stronger in the software. So we don't want this arm to go over 21.9 Newton meters. So now you got to play with loads until you get this moment down from 30 to 21, and you get this moment down from 31 to 21.9. So obviously they're going to be lower than these two. So I can play around with those loads until I get those two moments here. And I've now corrected for the duty cycle, and it's about 99 newtons here resulted in about 21, and 58 newtons in the right hand resulted in 28.1. So that's a lot of work to try to figure out how the duty cycle would affect the shoulder. But the nice thing is there's also, and I'll just show this here, that in fact, if you take 38.5 and you subtract 2/3 of a standard deviation, you're going to get 30.2 and 31.2. So that's why those values turned out to be that on this previous slide, 30.2 and 31.2. And that this 21.4 is about 70% of that, and this 21% is about 70% of that, which is what we want it to be for that duty cycle. But 3D static does have a nice little part in it here. If you ever looked at the fatigue analysis, what the fatigue analysis does is it says, what is a load as a percentage of an average person's strength, a weak person, a 25th percentile female strength, and a 5th percentile female strength. So here we can see that you could just basically pull up this window, and if your duty cycle said that you didn't want to exceed 70% of maximum, then you could just put loads in until this 25th percentile female was at 70% of her maximum. So you wouldn't have to do all the steps I saw here, or I did here. You could actually, instead of using the strength table, you could just say, what is the duty cycle? What's my maximum acceptable effort? And then, for example, for the left shoulder, what loads can I put in here to keep this under 71%? So that's a little trick that's in there as well. And here's for the right arm, here's that 70% as well. So what I want to show you is just a quick introduction to my handpack software with the time we have remaining. And the reason I'm showing is that again, you can go pull some of those references out, but I showed you in those large tables that there's many, many more references out there for other tasks that weren't tested in the Peebles and Norris, Grieg and Wells, and weren't presented in the Mitel tables. So instead of you all having to go out and read all these articles and compile all this data and keep up to date with it, as part of the consolidation of the work I had done with Ford, we decided to put this all into one software package. So basically the software works like this. This part's going to change because instead of picking one of 3 durations and putting in the frequency, you're going to put in a specific duration and a specific frequency like those examples we just did. and it's going to use my frequency curve to do the correction. So it's got acceptable values for different torques, and I'll show you some windows for that, different grips and pinches, and then also pushes and pulls, finger pulls, finger or thumb pushes, and pushes and pulls with grips, either with pinches or oblique grasps. You can decide what kind of units you want, what percent you want to design for, and whether you want to design for males and females. So for example, just to give you an idea of the data that's behind, if we look at pinches, these would be the different studies that I found for the different types of pinches. Some of them are, for example, chuck pinch. I got to use data from all of these studies. Maybe I could only use it from 3 studies or even one from Fernandez. And then I found data in the literature to correct these pinch strengths based on wrist posture. And I found some other data in the literature to correct pinch strengths based on aperture, so how far the fingers are apart. And we always have data from females, but in some cases we don't necessarily have data from males. But based on some of this, we can make some estimates of how much stronger the males would have been compared to the females. And then the old software, which I'm just revising right now, used to have a curve that came down like this to kind of mimic the connector data, and another curve that came down with frequency like this at longer efforts to mimic the hose data, and sort of an interpolated curve. But the new software, which will be coming out soon, will actually have just my consolidated curve with duty cycle at the bottom. So I've sort of shown you this kind of typical things on the side. For things like torques, you can decide on pronation, supination, the orientation of the forearm, corrections for elbow angle, and then all kinds of different interfaces based on the data in in the Peebles and Norris. I may just actually pull the software up here and show you straight up. So for example, with torques, pronation, supination, there are many different values, and they sort of have graphics to show it. This will be changing to include duty cycle as well. The different ulnar, radial, deviation, flexion, extension, are you in a power grip, a pulse pinch, lateral pinch. And this is about the only case where I didn't have any data, but I do have it for things like extension or ulnar deviation and radial deviation. With different grips, is it one-handed? Is it two-handed? How big is the span? What posture is the wrist in? What posture is the ulnar radial deviation? What posture is the elbow angle? And all of this is based on data from the literature. Pinches, again, different kinds of pinches, different apertures. It's corrected for wrist flexion, ulnar deviation, and again, duration and frequency. So for pushes and pulls, how are you pulling on this with a finger? Do you have a glove on? How much clearance do you have, which will determine how many fingers you can get in here? Is it a thick or thin ring, which will determine contact stress? Is it a thumb or a fingertip that is being used? Is it the pad or the tips? What's the wrist posture? Pushes and pulls with different grips, different postures. And again, I don't always have the same posture corrections because maybe there's no data on how ulnar deviation affects this or elbow angle. And then this one is a little bit different in that these values tend to be quite high based on research that we've done. And what it suggests is just because the hand can push with a certain amount of force, you're going to want to go into 3D static to make sure the elbow and the shoulder could withstand that force as well. And we've been sort of working with the Jack software to try to get this integrated so that it just kind of all gets done at once. And so the software itself has multiple aspects to it. Will give you an acceptable force based on data in the literature. It's currently being used by a number of companies, including Ford, GM, Chrysler, a number of tier 1 suppliers, Ministry of Labor, and a number of other groups as well. And so we've had good feedback with it. I've been keeping track of the new literature that has existed in the 5 or 6 years since I published the research or published the software, and a new version will come out with some big changes, especially to the wrist flexion and extension, pronation, supination component of the software. So with that, I would like to thank you for your attention. These are some of the funding agencies that have funded the research over the years. Particular shout out to Ford, who's funded much of the sort of filling in the gap research, as well as Auto 21 and the Center of CRE-MSD, the Center of Research Expertise for Prevention of Musculoskeletal Disorders. And with that, I would like to thank you for your attention, and I guess we may even have some time for questions.
Thanks, Jim. So if there are any questions, if you could use the Q&A box to put any questions in, that would be great. There's nothing there now. But maybe, Jim, could you address what happens if you have someone, say, in a job rotation situation where they're, doing one repetitive task and then they move to another? How could you then, or could you then use the equation for that?
Well, I'm working on trying to come up with something reasonable with that, and that is sort of the holy grail in ergonomics right now, is how do we combine tasks? And part of the Auto Partnership Canada research is looking at just that. I have a PhD student who's looking at trying to predict fatigue for multiple different tasks. So for example, instead of going to 30 and coming to 0 and going to 30, maybe you go to 30 and then you go to 50 and then you go to 0 and then you go to 20. So trying to simulate more and more complicated tasks, trying to estimate fatigue, and then we've got some physiological models that we're working on to try to predict instantaneous fatigue levels and how different combinations of tasks would combine. And then I'm going to back calculate how my equation could be modified or used in a way to combine those tasks. But no one's really done that research yet. But I have a PhD student who just proposed, and we're literally starting next week on some studies to see if the methods we have can be refined to do that. But yeah, that's a very good question.
Great, thank you. So I don't see any questions so far, but don't be shy. Feel free to enter something there.
So I will enter my email address if anyone has anything specific. I will be getting slides to to Margot, and I'll also have a reference list there just in case there's some things that you want to get a hold of. But I will, at least if you need to contact me directly, put my email in here.
Okay, that would be great. And what we'll do is when I post the recording, I have that put a webinar page now up on the website that's changed a bit from a week ago. So all the webinars that we do, there'll be links there and access according to membership level and fees and so on. But I'll post the reference list with that so that you'll be able to access the recording, hoping that it worked. I think it did. And also the references all in one place. So that should work well. Jim's address just went by, but I'll put that up on the, I'll put that up on the information as well.
Okay, to answer Wendy's question, I've sort of promised GM I'll have the update done by the end of the month or within a month. So I'm hoping to be early November probably the update will be finished.
Great. So we can post the information. If you're interested in HandPack, I can put that on with the webinar information as well so that you've got access to contact Jim for that.
Yeah, I'll put a website on that last slide there when you get the, my website's been down for today, so I can't give you, if I give it to you today, you wouldn't be able to get it up. I need to update some information. So, but it should be up by Monday. So I'll try to get that stuff to you, Marco, today or tomorrow.
Great. There's a question there about the cost to get a license.
Yeah, it's similar to 3D static. It's about $950 for a license, and then after multiple licenses, it goes down in price per license.
Okay, I don't know if you can see that question that Ruth has just put up.
Yeah. Yep. Yeah, I mean, I teach hazard checklists in my course, and obviously they have a role. Rula, again, I think is a good screening tool, but it doesn't have hands on it. So it does have some things related to neck risk, which other tools don't. But I would tend to use these checklists to determine which tasks you might want to do more detailed analyses, like the ones I was talking about today. Um, and so, yeah, and to go to Arita's question, the Ergo Solver, so basically the Ergo Solver has my frequency and duration corrections. In fact, my company developed the Ergo Solver, what we called the Force Solver, for Ford originally, and then now it's been incorporated into Jack. So the solved hand forces, if you choose to include the frequency correction, they are included in the solved forces. So I'm not sure if the example I had that checked off, so they may have already been solved forces, but I was just trying to show that as an example. A good question about age differences. It definitely has male and female buttons, so you can pick whether or not you want to design for males and females. I've had some good questions lately about trying to account for age. Typically, the MOL here in Ontario designs for the generic population, but some companies with an aging workforce are starting to ask about the software maybe having the functionality to say, well, if this is what a young person could do, what could someone in the 50 to 60 range? So it might not be in this version, but I'm certainly starting to consider how to incorporate age into these predictions. So the question from Elizabeth, it's hard to know what the frequency or the durations of the lifting were. I've made some efforts to estimate that, but certainly things like the Snook tables do incorporate lifting and frequencies and acceptable forces for given frequencies throughout a day. So I think that that's a good solid database, and you can see that that data matched up quite well with the correction factor I created based on upper extremity. Thank you, Sue.
I think there was still some typing going on there, so we'll give it a minute.
So good question from Andrew. As I showed you theoretically, let's say I had to do 1,000 lifts in a day or 1,000 hand grips. Right now, we don't have a good method. We're hoping that our fatigue prediction model will get at this, but if you decide to do all 1,000 in the first 2 hours and not do anything for the rest of the day versus spreading them out, we know that you would be more fatigued if you did it all at the beginning of the day. But we don't have a good method to account for that because things like the Snook research and our psychophysical research all sort of had people do things at set beat times and with constant intervals in between. But again, we're hoping that this fatigue model that we have will be able to say, well, what would the fatigue accumulation, kind of what we'd like is like almost like a fatigue thermometer through the day based on the time history of a moment, let's say at the shoulder or the hand grip, to say, okay, this is fatigue, okay, this is where you'd be after the break. And I think we'll be able to show that if you do everything at once, you will accumulate more fatigue even after the remaining 8 hours or 6 hours than you would have if you spread things out. But so it's very worth considering it. It's just we don't have a lot of great methods to account for it right now. So Sabrina's question. So typically when we do these single effort maximums, they're like 1 or 2 seconds with a peak effort. So they typically they wouldn't be throughout a period where fatigue would occur. If you do multiple ones, then fatigue may be an issue for later efforts. But we call it a maximum voluntary effort because it's what you're capable of doing maximally from a voluntary point of view. We know, we hear about women picking cars up to get their children out. We know that muscles can be driven to higher levels than we allow them voluntarily, but typically that would cause damage. So we typically can't, we have inhibition that prevents us from doing that. So what we get during a 1 or 2 second maximum is what we call the maximum voluntary strength. We know muscles are capable of more than that, but that's kind of what becomes our baseline. So the duty cycle, in terms of Jacques' question, I would propose the duty cycle is a better way to evaluate repetitiveness than frequency. And in fact, my whole maximum acceptable efforts is based on duty cycle because it both combines the duration of the efforts, and how often they're being done. And you could see in the slopes of those connector and hose study data, things were being done at similar frequencies, but there was a much bigger drop off in the hose insertion data because those efforts were of a longer duration. So I think duty cycle, and Richard Wells was one of the first people to sort of propose this, is the way to evaluate the repetitive level of a task, in lieu of us eventually being able to combine tasks or determine how the allocation of rest breaks, even for a given duty cycle, can affect a task. So you could have a 50% duty cycle that you do on off all day, or you do the whole task for 4 hours and do nothing for the next 4 hours. The first will probably be less fatiguing, but my method right now doesn't really account for that. It really, about the longest effort you'd want to use in my equation would be maybe 7 or 8 seconds. It may work a little bit beyond that, but I don't have data to confirm that.
Okay, looks like there are no other questions right now, but feel free to email Jim if something comes up to you. Oh, okay. There's some typing going on now, so hold on.
Jock's got a follow up. You, John.
I think there's one more coming.
Well, I don't know if I want to get into that political question. Um, I mean, I think that we have to do the best evaluation that we can, and we have to make a decision. But they're not perfect. They're not perfect evaluations, but we just try to bring as much science into it as we can. And if it finds that the task is acceptable or unacceptable, that's that sort of black and white decision that has to get made from a very gray, complex situation. 100 years from now, we'll probably be able to do a better job of doing these evaluations. But what I'm trying to show today is this is the best data that we have available, and sort of how we can use it in a responsible way. Thank you, Kathy. Yeah, I mean, I don't like to get into the term repetitive because I think it's just a semantic thing. Really, it's, is a task, is it demands on a muscle or tendon, are they acceptable or not acceptable? A lot of people get caught up in the term repetitive, a lot of stuff based on Barbara Silverstein's research, but even she was just trying to bin people into two different groups. She wasn't saying that all repetitive is bad, or that low repetition but maybe high duty cycles is good. So I think we need to move away from kind of whether something gets tagged repetitive or not repetitive, and actually look at the specifics of the job, the demands, the frequencies, the durations, and combine all that into our evaluation. So I try to avoid that term repetitive because I think it's a bit of a red herring when it comes to ergonomics. Yeah, I mean, one of the things about this software or 3D static or whatever is it tells you what healthy people can do. So, but what some of the WSIB folks have done is said, okay, well, maybe based on a functional abilities assessment, we can find what percentile this person is right now. For example, their shoulder maybe is at a 10th percentile strength. So then we could use something like 3D static or handpack to evaluate what is acceptable to 10% of the male or female population, to try to turn it from something that's more a population-based tool to something that can at least be manipulated to be used by people like WSIB or rehab specialists to determine, what would be acceptable to that individual on that task given their current physical capabilities. So I think it might help with WSIB restrictions, or at least evaluating whether someone would be restricted on a particular task, given a disability that they're partially, let's say, recovered from.
Okay, I think we're at the end of our time now. So thank you everyone for participating. Thank you very much, Jim. Jim, if you can just stay on for a couple minutes with me, that would be great. Just want to catch some of the slides. I think I missed two at the beginning there to put onto the recording. Oh, there's some typing going on again now. Okay, so yeah, thanks everyone for participating. Have a great afternoon. Hopefully you'll be able to use this information in whatever you're practicing in ergonomics. And I think that is it. So you can just close down the screen and that'll log you out. Again, Jim, if you can stay on, that would be great. Thanks so much. Jim, can I get you just to go back
Thanks,
to the
everyone.
start of your to the start of your presentation? I'll be sending out the information on how you can access the recording once I have it up. So that should answer that question for Rachel and anyone else. But if you go to the ACE homepage, the ACE webinars on the homepage, link to that. That'll take you to the webinar page and eventually the link.
I'm Jim Potvin. I'm a professor of ergonomics and biomechanics at kinesiology at McMaster University, and also the president of Work in Progress Ergonomics. Today I want to talk about how to use specific data from the literature and some correction factors to get specific values for upper extremity tasks, especially tasks that have repetitive demands or prolonged demands. So just to give you an idea of what we're going to do, I'm going to go through sort of a typical force posture repetition spiel on risk factors. Just give a little introduction to upper extremity anatomy and typical injuries, just so we're all on the same page. I do want to talk a bit about some muscle physiology and how muscles fatigue. I think that's important in understanding why certain tasks fatigue more than others. And then I want to break it into sort of how to determine the demands on tissues, specific demands, maybe using force gauges, and then how to determine capacities and quantify that, both for single efforts where maximum strength might be the limiting factor. We'll look at some software available for shoulders and arms, and then also some data from the literature available for hand, wrist, and forearm. But then I think what you're mainly here for is to try to get a better sense of how to get specific limits for repetitive or prolonged tasks. So again, we'll talk a bit about muscle fatigue. I'll talk about some of the previous methods to determine how much rest would be required for a certain, to recover from a certain effort for some duration. That many of you might understand that as the Romer equations. Talk about some of the good psychophysical research that's been done, especially on upper extremities, and those are simulations of specific tasks that can give us a good idea of what is acceptable. And then I'll present for you sort of an equation that I've recently published and developed, trying to determine maximum acceptable efforts as a percentage of maximum strength based specifically on duty cycle. And then I'll show you some handpack software that I've developed, which kind of brings in all of the literature that's out there in a place where you can find it easily, because I know it's difficult for most of you to keep up with the literature and even not always have the expertise to determine what's good data and what's not. So first of all, let's kind of just do a general. You wouldn't have an ergonomic talk without sort of these three risk factors being defined. As a biomechanist, force is really the one that's most important to me, but there are some modulating effects. So first of all, posture. There's two different ways posture can affect the forces that will damage tissues. One is if you get into certain postures, you may have pinching or occlusion on tissues that wouldn't be there normally. So we'll see later how the bursa in the shoulder, for example, is unloaded unless you sort of rotate your arm more than 90 degrees, and then it can be pinched. And so getting in those postures is more dangerous than not being, because it causes forces on a tissue that don't have to be there. The other thing is, of course, if you hold a load, you want to hold the load close to your body. If you get in a non-neutral posture, that load will create a moment that requires muscle forces that don't necessarily have to be there if you're in a more optimal posture. So postures can actually change the amount of force on tissues. when it comes to repetition, we'll see that force isn't the only thing important, but what is acceptable as a force will actually depend on the repetition and duration, and we'll get into the importance of duty cycle later. Both because repetitive forces may cause progressive damage to tissues or prevent recovery in muscles, and so the interaction between forces and repetitions becomes important in terms of determining what is acceptable in a work task.
Okay, I think that's good.
Is that good there? Or? Okay.